In this video, we'll be covering section 9.5, the dot product. This is going to be our last section that we cover in chapter 9. In this section, it's kind of a big one. There's quite a few objectives here. We're going to start off by defining this thing we call the dot product. It's just a new operation that we can apply to vectors. And using that, we will then use the dot product to be able to find the angle between two vectors. We'll be able to use the dot product to determine if two vectors are parallel and whether they are orthogonal. We'll define what that means later on. And then probably the most important thing is we will take a vector and decompose it into two different vectors that are orthogonal to each other. And then we will use this concept to calculate what we're going to call work, which is a concept from physics. So this is a pretty big section, so buckle up. There's this one probably going to take a little bit longer. So let's start with the dot product. So suppose we have two vectors. The vector v has components a1 and horizontal components of a1 and vertical component of b1. And I see right here there's a typo. This should be a j. Hopefully that's already fixed in your notes. It looks like it is. Okay, w is the vector then a2 for the horizontal component and b2 for the vertical component. The dot product of those two vectors, all you have to do is multiply their horizontal components, multiply their vertical components, and add them together. This dot product is a binary operation defined on two vectors. Binary operations are things like multiplication and addition, but this is a new binary operation that is only defined for vectors. Some texts call this the scalar product of two vectors or also the inner product of two vectors. So let's see how that works down below here. We want to do v dot w. So according to what it says above, all we need to do is multiply their horizontal components, 2 times 5, multiply their vertical components, -3 times +3, and then we add these two things together. So we get 10 minus 9, which is 1. The dot product of v and w is just 1. All right, let's say we reverse that and do it in the other direction. In other words, we're checking to see, is it commutative? Does the order matter when you do the dot product? So you can probably already imagine what the answer is, but let's just write it down. This would be 5 times 2, horizontal component of w, multiplied by the horizontal component of v, plus vertical component 3, multiplied by the vertical component, which is -3 for v. So that is 10 minus 9 again, and you can see it is 1. So it appears, yes, indeed, the dot product is commutative. All right, let's try a few more. You can take a vector and you can do the dot product with itself. So in this case, this would be 2 times 2. That's the horizontal component of v multiplied by itself, and then plus a -3 times another -3. So we would get 4 plus 9, which is 13. So that is the dot product of v with itself. Let's do the same thing with w. So if we dot product w with itself, we could just write that as 5 squared, 5 times 5, plus 3 squared, which is 25 plus 9, which comes out to 24. Or sorry, 34. Okay, now over here I have the magnitude of these vectors. So why do I have this here? Well, let's do the magnitude of v. Remember, the magnitude of a vector is the square root of its horizontal component squared plus its vertical component squared. So in this case, that would be for v, 2 squared plus -3 squared. And we get here the square root of 4 plus 9, which is square root of 13. And the reason we have this here is, look at the connection. You're doing the same computation. This is just missing the square root. So let's see if the same thing happens with w. So we're going to do square root of horizontal component squared. Well, that's exactly 5 squared. And then the square of the vertical component. So you can see again that it is indeed going to work. This is a 4 here. This is the square root of that. So another way to write this is if we do v dot v, if you do the dot product with itself, it's the same as this thing squared. It is the magnitude of the vector squared. So this is another property that's going to be true in general. So we've actually shown two now. We showed that the dot product is commutative, which I believe is on the next screen. Dot product is commutative. And we also proved that if you take a vector and do the dot product with itself, it's the same as the square of its magnitude. A couple other properties that are true. The inner product or dot product, it distributes over vector addition, which is what we would expect to happen. And that if you take the zero vector and you dot product it with any other vector, you do get the zero, you get the zero scalar. So that's the zero vector, where that's just the number 0. Okay, this down here is just proving this fact in general. Let's go ahead and move on though. Okay, so I said that we can use the dot product to find the angle between two vectors. So this next thing is going to illustrate how that actually happens. So suppose you have two vectors, a vector u and a vector v, and we're going to define the angle between them to be theta. Now, in order to come up with the formula we're looking for, we're going to change this thing into a triangle. So what we're going to do is we're going to draw the vector that starts at the terminal point of v and goes back to u to make this into a triangle. Now that turns out to actually be the vector u minus v. To show why that's true, let me actually draw in negative v. So that vector I just drew there is negative v. If I put that on the end of u, if I want to do u minus v, I have to follow this path here. In other words, let's change it to red here. This vector that starts here and goes up to here, that is u minus v. And you can see those two vectors are actually the same thing. Okay, so we have this triangle. Let's get rid of the drawing I have there. And so let's apply some trigonometry to it. So the known quantities would be u and v, and theoretically, right, let's just say we know what theta is. So the setup here would be side angle side. We have two sides of a triangle, and we have the angle between them. So that means we can use the law of cosines. Now, when I say we have the sides, you should be thinking of the sides as the magnitudes of each of those vectors. So the three sides of the triangle would be given by those three magnitudes. So if we plug all of that into the law of cosines, and we have cosine theta on this side, which means that it's got to be this thing squared on the other side of the equation. So here's just plugging everything into the law of cosines. Now let's use some of the properties from dot product. This is a vector. We're taking the magnitude of a vector and we're squaring it, which means we could express that as a dot product. Right, that was property 4 on the previous slide. Similarly here, we could represent this with a dot product, and then we can represent that with a dot product as well, and then we'll just leave this the way that it is. So now, if we apply the distributive properties, can kind of think of it like foiling. It's not exactly foiling, but applying the distributive properties to this will simplify down to this expression here. This is first, outer, inner, and last. And now if you look carefully at it, you can see we have some cancellation. This is going to cancel with this. Remember, these are numbers now. Dot product just turns two vectors into a scalar, turns it into a number, and this will cancel with this. I guess I actually didn't do that down till 2 steps below this, but what I did here is I used commutative property. These could be switched around and combined to give you this term here. And then I canceled all of these to give you this step. Divide both sides by -2, and that gives us this formula here. Now, this formula is useful in and of itself. It tells us we could find the dot product of two vectors by simply knowing the magnitude of each and multiplying it by the cosine of the angle in between them. Just an alternate formula for finding the dot product. If you knew the lengths and you knew the angle between them, you could multiply all of that together, and that would be equivalent to the dot product. But the other thing this formula does for us is we could solve this for cosine theta. So cosine theta in general is going to be equal to u dot v over magnitude of u times the magnitude of v. The goal, remember, was to get a formula for theta, so all we would have to do is take cosine inverse of both sides, and we would get theta from that. And that's what you see here. Okay, so let's apply that formula down below with these two vectors here to try to find the angle between them. And I just noticed here another typo. That should be a minus between those two. Okay, so if we're trying to apply this formula, the first thing we need is u dot v. So the dot product of these two vectors is found by multiplying their horizontal components, which would be 8, and then adding the product of their vertical components, which is, looks like, negative 15. All right, and if you add those two together, you get negative 7. So the dot product, this numerator, is going to be negative 7. Next thing we need to do is find the magnitude of each vector. So remember, you get the magnitude by essentially using Pythagorean theorem. We're going to square the horizontal component, which would be 16, square the vertical component, which would be 9. So we get square root of 25, or just 5. And then we need magnitude of v as well. All right, so for that one, we're going to have this square root of 4 plus 25 again. And that's square root of 29. All right, that one doesn't simplify, so we'll leave that there. Okay, so we're going to do cosine theta is equal to the dot product, negative 7, divided by the product of the two magnitudes, 5 times the square root of 29. Okay, then to get theta, all we need to do is take cosine inverse of both sides. So theta will equal cosine inverse of negative 7 over 5 square root of 29. The problem did not say whether to give the angle in terms of radians or degrees, so let's just do degrees. If your calculator is in degree mode, this should come out approximately to 105.07 degrees. You can see roughly looks about right. It looks like an obtuse angle in the figure up above. So that's how the dot product can be used to find the angle between two vectors. Okay, so let's go back to the dot product for a second. What is the dot product actually telling us? Like, what is it geometrically telling us? Well, if we take the formula that we just had, remember that it could be rewritten in this form here. We can multiply this denominator back over here. So the dot product is equivalent to doing the product of the lengths of the two vectors multiplied by the cosine of the angle between them. So let's look a little bit closer. Let's say these are the two vectors. We've got u, we've got v here, and then here's my angle theta. For right now, I want to call this side x, just the length of this thing here x. So where I got this from is I just dropped an altitude down from the terminal point of v onto u. So this has a fancy name that you see here. This is called the projection. We'll talk more about the projection later, but all it is just dropping a perpendicular down. Let's get an expression for the length of this piece here. To do that, we can just use right triangle trigonometry. We would have these two quantities, so I know that cosine of theta is adjacent over hypotenuse. So it would be x over the magnitude of v. Remember, the magnitude actually represents how long that is. So if I multiply this over, I would see that the length of that orange segment there is really the magnitude of v times cosine theta. So if we come back up to this expression, we see that right here. So this whole thing really says the magnitude of u times this thing that I called x. It's a product of two numbers. Anytime you're multiplying two numbers, you could think of that as representing some type of area. So if we come back to the picture, the idea is this. Imagine that we're going to form a rectangle. The base of the rectangle is going to be u, or really magnitude of u. And then the height of the rectangle is going to be the length of this side that I called x here. So that's why I have these tick marks. I'm indicating those are the same. So this is really x over here. So the dot product is really telling you the area of this rectangle that you see here. So that's one way to kind of interpret how this actually comes up. We'll see this concept of area show up a little bit later when we get to the work problems as well. Okay, so we found a way to determine the angle between two vectors using the dot product. So now we want to talk about parallel vectors, and then we'll move on to orthogonal. So we say that two vectors are parallel if they are pointing in the same direction or they're pointing in opposite directions. So if you had a vector here and you can think of them as basically coming from parallel lines, these would be parallel vectors. But they could also be pointing in opposite directions. All three of these vectors are considered to be parallel. Now, mathematically what that means is if two vectors are parallel, then there is some scalar that if you multiply the one vector by that scalar, it turns into the other. It's just a multiple, whether it could be a positive number, could be a negative number, but some number multiplied by that vector would turn it into the other one. So that's what we mean by parallel vectors. Now, suppose you had two vectors that are parallel. Suppose v and w are parallel vectors. In other words, suppose that v is equal to alpha times w. It's a scalar multiple of w. If we go back to our formula, then cosine of theta we know is equal to the dot product over the length of the two vectors. But we just said that v is equal to some scalar times w. So I've just replaced the two v's by alpha times w. In the top, we can apply property of dot products that allows us to pull the scalar out and just do w dot w. And then in the bottom, we can do the same property. When I pull the alpha out, it just has to go in absolute values. Okay, so then apply a property of the dot product that says if you do the dot product with a vector with itself, it's the same as the magnitude of the vector squared. And then in the bottom, this is precisely the magnitude squared. So you have the same thing here in the top and the bottom. Those cancel, leaving just alpha over the absolute value of alpha. If alpha is positive, then these two are going to cancel and you just get positive 1. If alpha is negative, then these two things are opposite, which means you would still cancel, but you would get negative 1. So the conclusion here is, if two vectors are parallel, then the cosine of theta, the cosine of the angle between them, is either plus or minus 1. Well, think about that for a second. When is cosine equal to 1 or negative 1? In a unit circle, cosine of theta is the x value, so cosine theta is equal to 1 here or here, which means theta is either 0 or theta is negative 1. Now, this is what we should have expected, because if in order for them to be parallel, the angle between them has to be 0, or it would have to be 180 or pi. So for example, in this case, the angle between these two vectors is 0. There's 0 rotation between them, whereas in this case, the angle between them is pi, or 180 degrees. So it's telling you what you basically would have expected. All right, so most of those things are restated here. We said if two vectors are parallel, then one of the vectors can be written as a scalar multiple of the other. Or you could say the angle between the two vectors is 0 or pi. Or we could simplify that and just say cosine theta, where theta is the angle between them, is 1 or negative 1. This, what's in parentheses here, could also be written a different way. We could say that if two vectors are parallel, then we know that the dot product divided by the magnitudes, the product of the magnitudes, has to be plus or minus 1, because this whole thing is the same as cosine theta. So it's saying the same thing here. And then the last thing is just the geometric interpretation. If two vectors are parallel, they either point in the same direction or they point in opposite directions. All right, let's check to see if two vectors are parallel. Now this should be pretty obvious because I've plotted them over here. You can see one is right on top of the other, so definitely they're parallel. But let's try showing it, and we're going to show it in two different ways. So in order for them to be parallel, v would have to be equal to alpha multiplied by some number. Well, you can pretty easily see what that alpha would need to be. If you let alpha equal 1/2, then 1/2 times w is 1/2 times 6i minus 2j, which is going to give you 3i minus j, which is exactly v. So that by itself is enough to prove that they are parallel, that v is a scalar multiple of w. There's a number that you can multiply w by, and it equals v. Okay, so that's fine, but sometimes that might not work well. So another option, you may not readily be able to see what alpha is. So the other option would be to look at the cosine of theta, cosine of the angle between them. Well, we know that that's v dot w over the product of their magnitudes. So let's just do all of that here. So the dot product in the top would be 18 plus 2, it looks like. 3 times 6 is the 18. Negative 1 times negative 2 is the positive 2. So that just gives us a 20 in the top. Then if we do their magnitudes, first one is going to be square root of 9 plus 1. 3 squared is the 9. Negative 1 squared is the 1. Times the square root of 36 plus 4. So if we simplify this, that is 20 divided by the square root of 10 times the square root of 40. So that's square root of 400. Square root of 400 is 20, so that whole thing just comes out to 1. If cosine theta, cosine of the angle between them, is 1, then they have to be parallel. The other way to think about it is theta would have to be cosine inverse of 1, which means that I guess I don't need to put that, but theta is equal to 0. Right? If cosine theta is 1, then theta has to be 0. So therefore, v and w are parallel. So two different ways that you could go about that. Check to see if one is a scalar multiple of the other, or check to see if the cosine of the angle between them is either 1 or negative 1. Okay, so we did parallel, so now let's talk about orthogonal. We say that two vectors are orthogonal if the angle between them is 90 degrees. So orthogonal is a lot just like perpendicular. It's kind of just another word for perpendicular. We just don't typically say vectors are perpendicular to each other. We would say vectors are orthogonal to each other. Lines can be perpendicular to each other, but vectors are typically said to be orthogonal if they form a right angle. So let's analyze this. Suppose that you have two orthogonal vectors, which means the angle between them is pi over 2. It's 90 degrees. Then we know that cosine of pi over 2 is 0. The x-coordinate for a point on the unit circle when you've rotated 90 degrees should be 0. But cosine theta is the same as this expression here. So that means that this expression is 0. If cosine theta is 0, this expression is 0. Well, we could multiply the denominator to the other side, but it's just going to wipe it out, which means the dot product of those two vectors is actually 0. So if you know two vectors are orthogonal, their dot product has to be 0. You can also go in the reverse direction. Suppose you know two vectors, they have a dot product that's 0. Well, the dot product is equal to this expression, which means then that this entire expression is going to be 0. And we know their magnitudes aren't 0 to begin with, so that means cosine theta would have to be 0, right? This is a product, so if you have a product of two numbers, think of this as one number, this is another number, you know the product is 0, well, the only way that happens is if this is 0. I guess the other way to think about it is just divide this over to the other side. If cosine theta is 0, then solve that equation. The only option is theta has to be pi over 2. So this means we have a biconditional relationship here. It says that two vectors will be orthogonal if and only if their dot product is 0. So it turns out it's much easier to check if two vectors are orthogonal than even to check if they're parallel to each other. All right, this little table here is just kind of describing what I was saying before. The words orthogonal, perpendicular, and then another one is normal. Those all are referring to meeting at 90-degree angles, but they're typically used for different objects. So when we say something is orthogonal, we typically mean two vectors. When we say two things are perpendicular, we typically mean lines or segments. And then normal is usually a combination. A line and a plane, or a vector and a plane is typically where you use normal. So you can have a normal vector, but we typically mean it's perpendicular to a plane. But for all intents and purposes, those three words are basically the same thing. Okay, so let's determine if these two vectors are orthogonal. So according to what we just said, we need to check v.w, and as long as the dot product is 0, then they will be orthogonal. Okay, so that's going to be 2 times 3, multiply their horizontal components, plus multiply their vertical components. And you can quickly see, yes, indeed, the dot product is 0, so therefore v and w are orthogonal. Their dot product is 0, so they're orthogonal. Okay, so why do we care about all of this? Well, one of the things we're interested in is sometimes forces can be decomposed into two separate forces. We've actually seen examples of this before. We saw this in the last section. So imagine we have a box, some kind of weighted box sitting on a ramp. The force of gravity is pulling it straight down like this, but the force of gravity gets decomposed into two orthogonal vectors. Some of the force of gravity is pressing the box against the ramp itself, and it's pressing against the ramp as a perpendicular vector. And then the other part of gravity is pulling the box down the ramp. These two component forces, if you added them, the resultant force would be equal to the force of gravity itself. So we talked about the example before of if you put a scale on a ramp and you stand on the scale, it's not going to give you your true weight because some of your weight is being pressed into the ramp, but some of it is deflecting down the ramp as well. So that's what we're seeing here. So in some instances, you might be interested in to know how much of a given force is being applied in a given direction. And that's why we would want to be able to break a force down into different components. So let's see how we go about doing that. So here's our goal. We've got a vector v and a vector w, both non-zero vectors, and let's say they have the same initial point v. So either one of these two pictures could represent it. This is the general picture, and this is the one that's a little easier to look at because I just have w on the x-axis here. So our goal is to decompose v. The only thing w is used for is going to basically be a reference. So we're going to decompose v into two vectors, v1 and v2, and these are the conditions. We want v1 to be parallel to w, meaning pointing in the same direction or pointing in opposite directions. We also want v2 to be orthogonal to v1. So these two have to form to make a right angle, but they have to add up to vector v. Okay, so what does that look like? Well, if we look at these figures here, these are all the different kind of scenarios that could come out of this. Here's our original vector v. This is the one we want to break down into two components. This is the vector w. So the first vector v, we want it to be parallel to w, meaning it's either right on top of w or it's going in the opposite direction of w, as you see in this case here. Now, once you have this vector, we need to make the vector v2 to be perpendicular to this one. But the tricky thing is the two vectors have to add up to v. And you can see in this case, they do actually add up to v. If I take, let's try that again. If I take this vector, and it's hard to trace here, and I move it over here, this would represent the sum of the two vectors, v1 plus v2, and the resultant would be v. So that picture is illustrating what we're attempting to do here. Okay, so we're going to give a new name to this vector v1. This is called a projection vector. So the way to kind of think about this is, at least the way I kind of visualize it is, imagine that the sun is up here, and it's shining light down, and it is directly above this point, so that if you drew a line straight down, you'd get a perpendicular here. Then there would be a shadow created by the vector v. That shadow is the projection vector. It is v being projected down onto w. And you can see the same thing would be true back in this picture as well. Put the sun directly over that point so that if you dropped a perpendicular down right here, that's where that shadow would start. This is the projection of v onto W, you just have to extend W in the reverse direction. So this is what we call a projection vector, projecting V onto W. You can see V is shorter, or sorry, V1 is shorter than V here, so there's a missing component to it, and that missing component, to make it so the sum adds up to V, is the vector you see over here. And this vector is precisely the difference between these two. If you subtract these two, obviously you should get V2. I mean, if you just think about the way we are already assuming that these two add up to V1 plus V2 adds up to V. So if I need a formula for V2, just subtract this over, right? V2, by definition, has to be V minus V1. Okay, so we need to come up with a formula for this projection vector. That's really the goal. And to do that, we're going to use the angle between them, which is going to be the same as the angle between V and W. Okay, so here's where we're going to come up with that formula. So remember, before we get too far, let's remember some of the conditions. V1 was parallel to W. V1 right here, parallel to W. If these are parallel, that means V1 is a scalar multiple of W. Some number times W has to equal V1. So we're just going to call that scalar alpha. The other condition is that V2 has to be orthogonal to V1, which means V2 is also orthogonal to W. Right, the angle between them, since the angle between V2 and V1 is the same as the angle between V2 and W, then they're going to be orthogonal as well, which means the dot product here has to be 0. The dot product between V2 and W is 0. Okay, so let's come back here. Let's do the dot product between V and W. Well, we defined these two component vectors to be if you add them, you get V. So I'm just replacing V by V1 plus V2. We've already assumed they add up to V. Okay, then we can distribute. So I distributed it through the product. Because V2 and W are orthogonal, this part is really 0. So we're left with just V1 dot W. The product of these two is really just the dot product of these two. Okay, but we said V1 is parallel to W, so we can write V1 as alpha times W. Right? We know V1 is really alpha W, so just substitute it here. Okay, so now we have the dot product of W with itself, and we proved previously that could be written as the magnitude of W squared. So we've got a new formula for the dot product. V dot W is really alpha times the magnitude of W squared. Now what this allows us to do is solve for alpha. Right? Alpha was this unknown constant, but now I can just divide this over. Alpha has to be the dot product of V and W divided by the magnitude of W squared. But then we can take this and plug it back into this thing up here. V1 is alpha times W. Well, here's alpha. So if you multiply alpha times W is V1. So this gives us our formula for the projection vector. Remember that we said the other way of writing this is V1 is the projection of V onto W. So that is, right there is the formula for the projection of V onto W, which we're calling V1. So it's a little bit messy. Gotta be careful with your symbols, but not too bad. All right, and then the formula for V2 is dead simple. V2 is just V minus V1. In other words, it'd be V minus this whole thing. V dot W over magnitude of W squared times W. We don't typically write all that out because it's easier just to do this. Okay, so all of that information is put here. V1 is defined to be the projection of V onto W, and this is the formula for it. And then V2 is simply V minus V1. So this is where it starts to seem really messy. There's lots of new symbols here. It's very technical, but once you get used to doing this, the math itself is actually not bad at all. Okay, now before we even do the math up here, I think it's worthwhile to actually geometrically think about what's happening with this. We can actually solve this particular example without doing any of the fancy formulas. Generally, you won't be able to do it because the numbers are really nasty, but this one is contrived to come out pretty nicely. So the idea is, we got this vector v, I want to project it onto w. So to do that, you would drop down a perpendicular. Now, notice that the slope of this line is 1, so the perpendicular slope would be -1. So I know that if I start right here, let's actually put it in as red, if I connect these 2 points, that is a perpendicular line. So that means that this right here, this vector, is actually v1. If I project v down onto w, meaning drop in altitude, that is v1. So, and notice I could go ahead and write down what its components are. That would be 2i plus 2j. So let's actually do the formula now and verify that you do get the same thing. Okay, so using the formula, we know that v1 should be v dot w over magnitude of w squared times w. So let's do the dot product first. We've got 1 times 1 is 1, plus 3 times 1 is 3. And then we need to do the magnitude and square it. So the magnitude is going to be the square root of 1 squared plus 1 squared. So that's 1 plus 1. And then square that whole thing, which is just going to cancel the square root. And then we multiply that by w. So we got the dot product on the top, magnitude squared on the bottom, multiplied by w. This gives us 4 over 2, which is just 2w, and then distribute it through 2i plus 2j. And you can see, same answer as what we have above. So then to finish it, we just need to find v2. And v2 is v minus v1. So we just need to take this and subtract this. So you're going to subtract your horizontal components, meaning you're going to have 1 minus 2 as the I component, and then 3 minus 2 as the j. Simplifying that gives you negative I plus j. And let's plot this. So if we come back over here, the horizontal component is -1, vertical component is +1. That is our v2. And notice, I don't know if I really addressed this well before, but v2 is always just the altitude here. It's just pointing back at v. This vector is the same as that vector there. It's just moved back here to a position form. So these two vectors, if we added them together, would give us the vector v. And we could verify that. We could just add these back, and you can see it is v, and clearly the angle between them is 90 degrees. So they're orthogonal to each other, and they add back up to v. So the way to kind of think about this, the way this is going to be used, is typically with forces. And so the idea would be if you're there's some kind of force being applied in this direction. I think maybe one of the examples I thought of earlier was, suppose you have a turbine, a wind turbine, and that wind turbine is, let's say it's located right here, and normally you would want to be able to rotate the turbine. But imagine that for some reason your wind turbine is locked in this direction, and let's say the wind is blowing in this direction. Well, some of the wind its force is being lost when it goes through that turbine. It's not going to be able to spin or apply as much force to the turbine as it could if it had been rotated directly in line with the wind. So the question is, how much of this force is actually being applied to the turbine? And that could be answered by looking at v1. This is the effective wind speed that the turbine is seeing. It's not seeing the full force because it's not turned directly into it. It's only seeing this much wind speed over here. So that's one way of kind of thinking about how this will work. Okay, so let's try a different application. Okay, so it says a wagon with 2 small children as occupants weighs 100 pounds and is on a hill with a grade of 20 degrees. What is the magnitude of the force that is required to keep the wagon from rolling down the hill? It's kind of similar to the problem that we saw before with the moving a piano up a ramp. Now, one thing I need to point out right away is that this figure that I took from our book is not actually drawn accurately. The fact that he's holding this handle at an angle actually changes the math that's involved, as we'll see in an example after this. So we need to kind of modify this. We need to make the assumption that he is actually pulling this completely parallel with the ramp, so that the math that we're about to do here actually works out. Okay, so the idea is that, let's change back to blue here, the force of gravity is pulling the wagon, pressing it against the ramp, but it's being broken down into two separate vectors. As this thing is pulling it down, some of that force is actually pulling you down this direction, and some of it is pressing perpendicular against the ramp itself. And the idea is these two vectors should add up to this vector here. Now, the problem says to find how much force it takes to keep pulling it up the ramp. Well, here's the idea, is that this is how much force is pulling it down the ramp, so the force that we have to pull up the ramp is the exact same vector pointing in the opposite direction. So the idea is, if we can find the magnitude of this vector, then that is how much force it takes to keep it pulling, to keep it stable, to keep it from going down the ramp. So the goal is just to find this thing right here. Okay, so to do that, let's define some vectors. Let's start with the force of gravity. So the force of gravity, if you imagine this being the origin right here, then the force of gravity, the magnitude of it is 100 pounds. And if this is the origin, this would be like negative 100. So we could define the gravity vector to be just negative 100 j. It's just pointing straight down. Let's also define the vector w. Now, w is just defining the ramp, so I don't actually care how long it is. So we might as well just make it a unit vector. Remember that any vector can be written in this form, where you have the magnitude of the vector and you have the direction of the vector. Oops. Oh my. All right, that's better. So we're just going to say, well, let's let the magnitude be 1, because who cares? All we need w for is a direction. So this vector w is really just cosine of 20 I plus sine of 20j. Right, that is the vector w. So what we want to do is we want to project this vector onto the ramp itself. So that projection means and I'm gonna use this endpoint for this just so it's a little bit bigger for you to see, even though it technically stops there. The projection would make this the force that's pulling down the hill, and that's the magnitude of that vector is going to be the same as what it's required to pull us up the hill. So this is really what we need to find. Well, that's precisely the projection of the force of gravity onto w. I know w is down here, it doesn't matter, you can put w up here. We are projecting this vector onto this line, and that line is defined by this. So the goal here to solve this problem is we need to find the projection of f of g onto w. Well, the formula for that was to do the dot product between them over the magnitude of w squared times w. Right, that is the formula that we have right here. Do the dot product between the two vectors, take the magnitude of what you're projecting onto and square it, and then multiply it by w itself. Okay, so we have everything we need here. So to do the dot product, we multiply their horizontal components. Well, this has no horizontal component, so it would be 0 multiplied by the horizontal component of this one, which is cosine of 20. That's all going to get wiped out anyway, so we don't really need it. Then multiply their vertical components. Well, this one has a negative 100 times the vertical component of this, which is sine of 20. All right, it's the product of the horizontals plus the product of the verticals. So that's the dot product. All right, on the bottom, you would do the magnitude. Now, you can go ahead and write all the work out for this if you want, but this is a unit vector, so the magnitude is just 1. If you don't notice that, then you can do the whole long thing. It would be cosine squared 20 plus sine squared 20 with a square root over it and a square out here. But sine squared theta plus cosine squared theta is 1, so that whole denominator is just 1. All right, and then we can put w out here. So cosine 20i plus sine 20j. So let's simplify this. Denominator's 1, this gets wiped out, so we just get negative 100 sine of 20 times cosine of 20i plus sine of 20j. So this represents the projection of the gravity vector onto the ramp. Now, to find what is the actual force that the wagon is, pulling down the ramp in this direction, we just need the magnitude of this, the magnitude of that projection vector. And you could, distribute this and do the whole long computation for the projection, but if you're careful and you notice, this really is just a magnitude multiplied by a unit vector. So the magnitude is just this thing right here, if you take the absolute value of it, right? This is a scalar multiplied by a unit vector. So it really is just the absolute value of negative 100 sine of 20. If you put that in your calculator, that comes out approximately to 34.2, and in this case it would be pounds. So 100 pounds of kids in this wagon, that 100 pounds pulled straight this direction. Some of the 100 pounds is pressing against the ramp here, and some of it is pulling down this direction. And the amount that's pulling down the ramp is 34.2 pounds. So we would have to pull with an equal force to keep it from sliding down that ramp. Okay, so that's the way you would solve it using the formulas here, but you could actually solve this just using regular trigonometry. The formulas are important, mainly because these formulas can be generalized to higher dimensions, but this particular problem, we could have actually solved it a different way. So let's try to make the picture. Actually, you know what? I'm going to put this on a separate slide. So give me 1 second here. Okay, so I've just brought the picture over here. We've got the force vector pulling us down here. Again, I've made it larger just to make it easier to draw on it. So let's actually move the picture out of the way here and put some more information in. So we know the angle here is 20. And if you were to extend this over, we'd have a right triangle here, which means this angle up here has to be 70 degrees. The force vector, we know that the magnitude of this vector is 100. So the magnitude, you can think of it just as the length of that segment. So let's just put 100 here. The goal was to figure out how much of this vector is being applied in this direction, the direction of the ramp. And that's where this projection comes in. If we project this vector onto the ramp, it tells us how much force is being applied in this direction. So in other words, we just need to figure out how long that segment is. Well, you can solve this with just regular old trigonometry. We got an angle, we got an adjacent side, and we have the hypotenuse. So we know x is actually cosine of 70, So we know that cosine of 70 is equal to x over 100. And then just solve this for x. You get 100. Oops, sorry. x equals 100 cosine 70. And that comes out to the same thing as before, 34.2 pounds. So why is this working? Well, remember that sine and cosine are equal at complementary angles. So this expression is the same thing as 100 sine of 20. And that is what we had before. That was the magnitude, doing it the long way here, that was the magnitude of that vector. So definitely quicker to do it this way, but I encourage you to get used to the formulas because, as I said, those formulas are going to work even in higher dimensions. Okay, the last concept that we want to talk about is the concept of work. So we're going to start off with an easy example for work. Suppose that we're applying a force to move an object and the force is applied in the exact same direction as the object. This would be the ideal situation. If you're doing work, you probably should try to apply the force in the same direction that you want something to move. So as an example here, got a guy pushing a car, and let's say it requires a force of 90 pounds for him to move that, and he moves it from point A to point B. He moves it 200 feet, let's say. Then we define the amount of work that is done by the magnitude of his force times the distance that he moved the object. So in this case, it would be 200 multiplied by 90, which gives you 1,800 foot-pounds. Right? Notice we're kind of multiplying the units as well, feet pounds, foot-pounds. So the work, 1,800 foot-pounds. Now, one way to visualize this geometrically is that you could think of it as a rectangle. Think of it as the force that he's applying. If I put it orthogonal to it and make this 90, then by multiplying them, we actually found the area of a rectangle here. All right, and this concept of area is going to come back to how we define dot product. We said the dot product could be thought of as an area of a rectangle. Well, work can be thought of as a dot product, so it brings area back in. Okay, so that's a pretty easy example. If the force is being applied, as it is in this case, in the direction, the same direction, the force vector is going this way, and the car moved that same direction, then all we have to do is multiply the force by the distance traveled, and that's work. But there are some situations where you apply a force not exactly in the same direction that an object is moving. So let's say we've got this guy here, and he's trying to push this filing cabinet, and for some reason, he's holding his hands way up here, so he's applying a force in this direction here. But the object is moving horizontally in this direction. Well, so what's going to happen here is some of his force, some of it's going to be lost, basically. It's not going to be applied in the direction that we want. So in this type of situation, we define the work that is completed to be the force vector, the dot product of the force vector and the vector formed by the motion of the object. Now, it turns out that that definition is consistent with the previous. So the previous definition was just the amount of force in the direction of the object was moving, and in this case, all of the force. Back in the first example, when they're going in the same direction, when F is going in the same direction as the object is moving, this is the magnitude of F. All of F is being applied in that direction, and then you multiply it by the distance. In this definition, if we're going to define it to be the amount of force in the direction of AB, well, that's precisely what the projection vector means. If you take a vector F, and you want to know how much of this is being applied in this direction, that's what the projection vector is. So the amount of force in the direction of AB is the projection of F onto AB. If we take the magnitude of that, that's going to give us the length of that vector. And then the distance vector, the length of the distance would just be the magnitude of that vector. If you then put this into the formula that we came up with, remember the formula was the dot product between the two vectors divided by the magnitude of this vector squared, and then it would be multiplied by the vector AB. But then we are doing the magnitude on that. So that's where this magnitude came in from. And so now you just get a bunch of cancellation. These two could be multiplied, and when these are multiplied, it's the exact same thing as this. Magnitude of AB squared, this is the magnitude of AB squared. So all of that just cancels, leaving the dot product. So this definition is consistent with the car definition that we did before. Okay, so let's try to apply this example. So we have a girl is pulling a wagon with a force of 50 pounds, and the question is how much work is done in moving the wagon 100 feet if the handle makes a 30-degree angle with the ground. Well, you might think that what does the angle that the handle is at make a difference? Isn't it going to be the same amount of work either way? Well, it turns out that in order to move the wagon, it's going to require a greater force if the angle is not completely parallel with the ground. Because what ends up happening, if this is the force that she's pulling here, then the effect of that force is actually the projection of this vector down onto this horizontal line. And you can see this is not as long, so there's not as much force being applied in this direction as there is in this direction. So therefore, she is actually going to pull harder for it to be up at a 30-degree angle. Okay, so I've taken the given information and we put it into this figure here. So this vector represents her force. We know she's pulling with a force of 50 pounds, so its length is 50. We know the angle is 30 degrees. So to get the work is force dot product with the motion. So the motion vector, AB, well, it's labeled as AB for now. We can write down what that vector is. AB is the vector that would go from 0 out to 100. So that's just 100i. There's no vertical component, so 100i is the motion vector. And then we can write down what f is. The vector for f is the magnitude of f, which is 50, multiplied by the unit vector that represents the direction, meaning cosine of 30i plus sine 30j. Right? We've got the magnitude times the unit vector that has the same direction as f. Okay, so we just need to do the dot product with these. I guess we can simplify this one first, so let's do that. So this would be 50 times cosine of 30 is radical 3 over 2 plus 50 times sine of 30 is going to be 1/2 j. So we've got 50 radical 3 over 2i plus 25j. Alright, we need to do the dot product with these two vectors. So that's what work is, simply the dot product between these two. So we multiply their horizontal components, which is going to be 100 multiplied by this. So 100 times 50 square root of 3 over 2. That's multiplying the I components together, plus the vertical components. Well, this one doesn't have any, so it's 0 times the 25. Well, obviously that just goes away. So we get the product here, which is going to be, if you divide that by 2, that's going to be 50, which means you got 2500 radical 3. You can multiply that out, but this is the exact amount. And the units for this are going to be foot-pounds. It was the force was in pounds, and the distance was given in feet. So this is foot-pound. And that's it. So again, the idea here is that she was pulling with a force of 50 pounds, but the net effect of her force was not 50 pounds. If we come down here and find the magnitude of this vector, which would just be this number that you see here, right? That's the length of this, 50, or really just we could say 25 radical 3. And 25 radical 3 is approximately 43.3. So even though she was pulling with a force of 50 pounds, the actual effect on the wagon itself was seeing a force of 43.3 pounds in this direction. Right? It was also feeling some force in the vertical direction because she's kind of pulling it up as well. But in terms of moving it horizontally, that's all that was being applied to the wagon. Okay, I believe that's the last example. Okay, so complicated set of notes. The problems will be a little trickier at the end because you are dealing with word problems. So again, make sure you're emailing me, and we'll see you on the next one.